Hugging Face have just released a dataset called Fineweb Edu. It's a dataset based on Common Crawl, so scraping the internet, that's then been heavily filtered and further filtered with the help of Llama 370B. Now this gives probably the cleanest dataset that's available in open source form today. I'm going to talk through the data processing pipeline to generate this dataset. I'll make some comments on what aspects of the filtering might be used and responsible for the good performance that Llama 3 and Phi 3 have achieved. Last of all, I'll give you my specific recommendation on what exact split to use of the Fineweb dataset if you want the best performance in pre-training. I'm going to talk a little bit about Common Crawl, what makes up the base raw Common Crawl dataset. I'll talk about the key datasets that have emerged in open source to date, like C4, for example, RefinedWeb used to train Falcon. I'll talk briefly about the performance as benchmarked by Hugging Face when they were building out the Fineweb dataset. Then I'll go through the basic data pipeline, bringing you all the way from extraction, then through language filtering, some quality filters, then some deduplication, and lastly, using a language model to further improve the filtering. In fact, I'll talk in detail about that LLM assisted portion of the pipeline, and I'll make a few comments on how that may have been used in developing, that kind of approach may have been used in developing Phi 3, Llama 3, and Fineweb Edu, which we know the approach was used for Fineweb Edu. Last off, I'll give my recommendation on the best filtered Common Crawl dataset to use. Unsurprisingly, it will be a Fineweb dataset, but I want to be a bit more specific on how you might hone in on a specific split of that dataset for best performance. To get started, Common Crawl is a non-profit organization that crawls the internet, and they have dumped the internet's contents for public use about 97 times now, if you include the May 2024 crawl. So this data is available on the commoncrawl.org website, where you can select any one of these crawls. And you'll see the format has remained consistent roughly since 2013. Before that point, the data, as I understand, was formatted a little bit differently. Now, if you filter down any one crawl, so say the crawl from May 2024, what you'll find, and it will obviously depend on how you filter it, but you can think of this as having about 200 billion GPT-2 tokens. That's tokens as measured by the GPT-2 tokenizer. Won't be all that much different if you consider tokenizers from GPT-3, for example. So that means across about 97 or say 100 crawls, you have about 20 trillion tokens of data if you filter down each of those crawls and you add them all together. Now you should note, and we'll come back to this later, that there's a very, very high overlap in the data that's there between every crawl. So in a new crawl, many of the websites that have already been indexed are recrawled. So there's a really high overlap between each one of those crawls, and that will become important later when we talk about the best approaches for deduplicating. Something that's particularly interesting is that if you look at the crawls one by one, they seem to improve over time. You can take a look at this graph here, and maybe I should just show you the full screen. You can see crawls that have been compared in terms of performance. Now, how is that done? It's done by training a small model, I think about 1.6 billion parameters using the Nanotron library. And by training the same model, but with different data sets, one can compare the performance. And this is an aggregate score. It aggregates across many different metrics like HeliSwag or MMLU. So there are a range of metrics that are chosen and then aggregated. And what you can see here is the improvement in the quality of the data as measured by these benchmarks over time from 2013 all the way up to 2024 today. Now, I don't want to overemphasize the improvement here. We're going from a range of 0.42 up to 0.435, maybe a little bit higher than that. So seems to be some improvement, but not to overemphasize that. Now, this basis, the Common Crawl dataset, has been used to build many filtered datasets therefrom. Some of these you're going to recognize, and I've put the names of a few big ones to the left-hand side. So first, there's the C4 Common Crawl, which was developed by Google, and this has got about 172 billion tokens. It's based on a single dump from April 2019, so it just includes one snapshot in time, and it's filtered using a range of rules that we'll talk about a bit later. This data set, even though it's from 19, is still very good It's probably about as good as RefinedWeb, the Falcon dataset here, which is quite a bit more recent. And it's even not that far off of the Fineweb dataset that's been released, although it's below Fineweb Edu, which I'm going to talk about later. Now, one difference with Falcon is that it's larger, and it's larger because it includes multiple dumps. So it includes, as I understand, all of the dumps from 2013 right up to maybe 2023. And those dumps are then very heavily filtered in order to get down to 500 billion tokens. Next, I want to take a look at some of the datasets that are used out there, including datasets that are not commercial but underlie some of the well-known open source models. So first of all, we have the C4 dataset, which was developed by Google. It's 172 billion tokens, and it's based on a single dump from April 2019. Now, this involves using heuristics, which we'll go through later, that are quite effective because C4, even though it's from 2019, it performs roughly the same as RefinedWeb, which I'll talk about. And it's actually pretty similar, maybe a tiny bit behind the 15 trillion Fineweb dataset that was created by Hugging Face in 2024 rather. Now, Falcon, which was based on the RefinedWeb dataset, open source and available on Hugging Face, is a 500 billion token dataset. And it's larger because it includes data from multiple dumps. So it's including, I think, a full history from 2013 up until 2024. Now, if it included all of those dumps in their entirety, it would be much, much larger, but it's been heavily, heavily filtered down to a size of about 500 billion tokens. Now, I've listed here 3 commercial models. These are not data sets, they're models because the data sets are not available, but I've listed them because I think they're interesting to make a few comments on. So first, there's Llama 2, trained on 2 trillion tokens. Of course, not all of those tokens were Common Crawl. There are also books and other sources included within it. Then there's Llama 3, which is a much larger data, which is trained on 15 trillion tokens. That's not to say the data set is 15 trillion because there are multiple epochs. But what's notable about Llama 3 is there's a comment in the technical report about using filtering, specifically using Llama 2 to filter out some of the better samples of the Common Crawl and probably other data sets in order to improve the quality of the Llama 3 model. Now, Phi 3, which is smaller than Llama 3, but at least in the mini form, it's about 3.5 billion parameters. It's able to perform like Llama 8B, a larger model that has been trained on more tokens as well. And Phi 3 in its report also alludes to language model filtering, notably filtering for educational content in order to improve the performance of the model. That brings us to the last 2 datasets, which are again open source. There's Fineweb, which is a 15 trillion token dataset that we'll talk about today. And this is a multi-dump dataset, so it uses all of the dumps from 2013 up to 2024. And that's one reason why it's much larger than, say, C4 or the RefinedWeb dataset. Then there's this effectively split or subsampling of the Fineweb dataset called Fineweb Edu. And this is a filtered version of Fineweb, filtered using a language model, actually Llama 3 70B, to pick out the samples that provide the most educational content. So this is Hugging Face's interpretation of what it means to do educational type filtering. And we'll go through that technique in detail. Now, just to note that this is not actually a single dump. It's based on multiple dumps, although it is possible to just download the Fineweb Edu dataset for one specific dump. And that actually is kind of interesting and something I will come back to later. Here we have the performance of the datasets, and you'll see right up top the Fineweb Edu dataset in pink. And next is Fineweb, and pretty closely behind is the C4 dataset, followed in green by RefinedWeb. So basically blue and green, RefinedWeb and C4. So the 2019, that's the C4 dataset from Google. RefinedWeb, that's the Falcon dataset from, I think, 23. Those two, both pretty similar in terms of quality. Fineweb makes a small improvement on that, but Fineweb Edu makes a fairly significant improvement above that by using a language model to filter. With that, let's go through the basic pipeline, and it's most instructive to go through Fineweb just because it's open source and clearly described. So I'll take you through all of the steps involved in getting from the Common Crawl dataset, which is what you see if you download this dataset here. Let's go to it actually. If you download this dataset here. And And I'll take you through the different steps in some level of detail so you get a feel for exactly what's been filtered out. And after that, I'm going to talk about the LLM assisted pipeline. So how do we get from the Fineweb dataset to Fineweb Edu? So the very first thing is to download the dataset from Common Crawl. You can see here, if I increase the size of my screen, here is the latest Common Crawl dump. Actually, this is the April dump here, which I think might be the one used in Fineweb or Fineweb Edu. And you'll see that there are different file types here. The ones that are typically focused on are the work files, that's web archive format. There's also this web text format, the WET format. Now this is a kind of ready-made text format, so it saves you doing text extraction. But generally when you read the papers on data processing, they find it's better to start with the raw work data here and then use a tool like Trafilatura in order to extract the text from the HTML. And that indeed is what is done in the Fineweb approach. So extraction is done with this library. It's a Python library called Trafila. I don't know if that's the pronunciation, but that tool is used to extract text from the work files. Next, there is a URL filtering stage. There's basically a blacklist of URLs that are to be excluded. And so you run code through all of the URLs in the database. Indeed, the URLs are indexed within the work file database. So you can just filter out a list of blacklisted URLs. The next step then done for Fineweb is language classification. Fineweb is an English dataset, so it will use a very small model. It's a small neural network that you can find, I think, from Facebook called FastText. And FastText will be run on, I think it's the first 3,000 characters or maybe 1,500 characters or words of each document. And based on that, FastText will recommend what it thinks the language is. And then every document that has a language score for English over, I think, 0.7, maybe it's either 0.6 or 0.7, anything over that threshold will be accepted and any other documents will be thrown away. So that's the language filtering step. The next step then is a series of quality filters. So I'll go through this in a little more detail actually. Let me do that now, because there are 4 sets of quality filters. And you can see these if you just check out GitHub Datatrove, which is the open source library used. It was developed by Hugging Face. You can find fineweb.py in the examples. And this is the kind of master script that's used in order to run all of the data pipeline. And you'll see here the pipeline itself. So first work reader, so it's reading in the work files, filtering the URLs, then using Trafilatura in order to pick out the text, then doing a language filter. That's with FastText, even though you can't see it here. If you dig into the language filter code, you will find it. Then there's the Gopher repetition filter, the Gopher quality filter, the C4 quality filter, the Fineweb quality filter, and then the files are written to text or written to JSON format. And after being written to JSON format, they go through a deduplication stage, which I'll talk about in a moment, but takes up the rest of this file here. So for now, let me just break this up. I've talked about everything as far as language filters. I'm going to talk about quality filters now, and then I'll talk about deduplication, which is kind of removing copies of the same document that are within the overall database. So for quality filters, there are these 4 filters that are set up here. Now, it's somewhat arbitrary how these are named. They're named as they are just for historical reasons of the techniques that were developed. So kind of layering C4 on top of the Gopher ones and then layering the latest Fineweb filters on at the end. But let's take a quick look at what each of these are. The first one is a repetition filter. And we can check out this chat here where I've asked ChatGPT to tell me more about the code. I'll just open up all of these so that we can quickly view them when we want. So here's the Gopher repetition filter, and I've got the code there, and I've just asked ChatGPT to tell us a little bit more about it. And I'll only highlight a few key points, but basically we're checking here for duplicate lines. We're checking for a certain percentage of duplicate words within those lines. We're checking for duplicate paragraphs, and we're checking for the number of n-grams. and too much repetition of certain n-grams. So an n-gram, say a 2-gram, would be just having 2 different letters within a word. A 3-gram would be having 3 letters within a word. So you can check all of those different sizes and see if there are too many of given n-grams within the text. So this is basically what Gopher filter is doing. The repetition filter is checking for repetition at a few different levels, particularly the line level and at the paragraph level. The next filter is the Gopher quality filter. And here there are a few rules that are just being used. For example, we're expecting every document to have a minimum number of words. If it doesn't, we'll throw it out. Make sure that it doesn't have more than a certain number of words, we'll throw it out. Check for word length. So if there's some word that has 50 different characters in it, there might be something wrong. So we can have a threshold where we throw out documents that are exceeding that length threshold, maybe a certain number of times. Same with the maximum average word length. If words on average are 50 characters, there's probably something wrong with the document itself. Something else to check is the maximum symbol to word ratio. So if there's a ton of these special symbols relative to just normal letters, there might be an issue. Too many bullet lines, too many ellipses, so lines finishing in ... If that's happening a lot, it's probably an incomplete data set. Here we're checking the ratio of characters that are not alphabetic. Again, can be a signal of bad text. And then we want to check there's a minimum number of stop words. So if there are no sentences finishing in a period, that might be a sign that the document is not particularly well written. So you can see here, the flow basically is to tokenize the text as necessary and then run this series of checks and throw out documents that don't meet these Gopher filters, as they're called. The next set of filtering is the C4 set of filtering. So C4 is again kind of a set of rules, and there are some kind of ad hoc rules that work out well for filtering. So for example, you may want to just remove citations. If there's Wikipedia style citations, you could pull those out. No terminal punctuation. So this is actually a very big filter. It removes a lot of documents, I think something like 30% or maybe more. This will take out if there are lines that don't have any punctuation to finish them off, and there's a certain threshold number of those lines, it's going to pull out that document from the data set. Next is minimum number of sentences, so enforcing a minimum number of sentences per document, minimum words per line, maximum word length, removing documents containing a certain number of lorem ipsums. So if the document is just repeating that, that's probably going to be an issue. Filter out lines mentioning JavaScript. This is because web browsers can have a lot of JavaScript that ends up being repetitive. And there's also a curly bracket filter. So if you have documents with curly brackets, that could also be a sign it's not going to have text that the language model can easily learn on. So again, this is a custom set of rules, but I'll say it's a very good custom set of rules because the C4 dataset from 2019 is still among one of the best open source datasets. And there is very little else that is used in C4 other than these rules here, with some deduplication I'll talk about later. So that's the C4 set of rules. And I think I should mention that in the Fineweb dataset, I'll have to check this, but I believe most, if not all, of the C4 rules are used, with the exception of filtering out based on terminal punctuation. It was determined that this removes too many of the samples, and so I think this specific filter may not have been used in developing Fineweb. Last of all, there's the Fineweb custom quality filter. So this is one of the last filters applied on the Fineweb dataset before deduplication, and it's what makes the Fineweb dataset be slightly better than C4. So if you remember going back here, you'll see that C4 is like slightly below Fineweb, and this is probably largely due to this final step of custom filters through Fineweb. And these filters are actually fairly simple. There are basically 3 things being checked. One is the line punctuation ratio. So it will check the ratio of how many lines have got end punctuation versus total number of lines. And if there is not a certain amount, it will clear out those documents. It will then do a check on the short line ratio, how many lines are below a certain length relative to the total. And it will clear out ones that are documents that are above a certain ratio. and then it will check for character duplicates and new line ratio. So there are basically 4 checks. Now, Hugging Face did a set of ablation studies on very many parameters, like tens of parameters, and they found that these ones here were the parameters that allowed them to improve performance a little bit. So again, you have a series of heuristic or empirical based checks that will reduce the size of the data set to improve the quality. So that's an overview of the filters that are used. As I mentioned, if you just look at C4, you basically have these filters here plus some version of these. And so it's the Fineweb filters that I just went over last. It's these ratio-based filters for documents that are providing a slight improvement in going from C4 up to the Fineweb filter. Now, with quality filters done, we're going to cover deduplication, which is one of the last steps in the pipeline. And this involves removing duplicate copies of the information from the dataset. And this improves the performance during training because it means the language model is not repeatedly seeing the same data and then forgetting some of the other data. So instead of the language model constantly seeing dog, 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 and forgetting some subtle detail, it's going to be limited in how many times, and it's hopefully going to stop overfitting too much on the samples that are there in very high frequency because they've been removed. Now, there are 2 ways of doing duplication that I'll talk about. You could come up with some more as well. But the 2 I'll talk about are the C4 based approach, which is sentence based. This is the Google approach in 2019, where they remove any 3 sentence repetitions. So they go through the full data set. Now remember, C4 is just being done on 1 dump, but they go through that full data set, and if there are instances of 3 sentences being repeated, they will just remove all but 1 of those copies. And that seems to work pretty well because C4 is a good data set. It leads to good performance on models. What's maybe a bit surprising is it means in the documents you're going to have segments where there are 3 sentences that are just removed in certain cases, and it will just leave a gap in the document. And I would imagine that probably is bad for continuity in the model's understanding from that piece of data. But empirically, C4 still seems to be a good data set. Now, Fineweb doesn't do that. Fineweb instead takes a min hash approach. And at a really high level, what this means is it's removing documents that are 75% similar. Now, the technique that's used in order to determine that documents are 75% similar or higher, it's a min hash type technique, which involves splitting the document into words, converting the words to numerical representation, doing a hash, doing multiple hashes, in fact, all over the document. This technique is a bit more granular, so I'll leave you to read the ChatGPT chat that I had earlier if you want to find out in more detail how that works. But suffice to say that it allows us to pull out any documents from a data set that have a similarity that's above a certain threshold, namely 75%, I think, in the case of Fineweb. Now, there's one pretty important point here, which is as to how deduplication is done, because Fineweb is based not just on 1 dump, but it's based on almost 100 dumps across time. So the final Fineweb deduplicates only within each dump. So it will just look at 1 dump and it will deduplicate there, and it will deduplicate separately within each of the separate dumps. Now you might ask, well, is it good to have copies across all of the dumps? Why don't you deduplicate across all of the dumps and only keep 1 copy across all of those dumps? And there's an ablation study that looks at that. I know there are 4 lines here, but if you focus on in orange, so at the top, that's the independent min hash. So that means deduplicating each dump at once. And then if you look at the green, which is the full min hash, this is where you deduplicate across all of the dumps, which will obviously remove a lot more documents. And what they found is that if you deduplicate across all of the dumps, you actually end up with worse performance. So you get better performance if you leave in the main documents that are in common between all of the dumps. And yeah, there are a few implications to this. First of all, it's better if you just deduplicate within the dumps. And that's why the final Fineweb here is indeed just deduplicated within the same dump. But if you only deduplicate within the same dump, it means you're going to keep way more data. So your data set is going to be a lot larger, and you're also going to have a lot more repetition across your data set. And what that means is if you're fine-tuning with Fineweb 15 trillion tokens, it's basically like you're doing many epochs, because you're going to be seeing the same data just across many of those dumps. And that's something that's important, and we'll come back to it a bit later on. Also, I think for me, it was a learning to realize that when I hear of a data set that's 15 trillion, it sounds to me like, oh, there's like 15 trillion of new information. But no, a lot of that is going to be repeated. So if you think about what's the unique information on the web, it's probably a lot less than 1 trillion tokens is my guess. Although correct me in the comments if you see things differently. But based on looking at the deduplication studies here, it seems to me that 15 trillions of token from Common Crawl, most of it is going to be quite similar. And that brings us through the full basic pipeline from extraction through URLs, language filter, quality filters, and deduplication. And that brings us to the Fineweb dataset. So that is the black line that's shown here and performs slightly better than C4. So having covered the pipeline for Fineweb, now the question is, how do we get the performance up to the level of Fineweb Edu? And the answer is by using a language model to filter out the better samples. So the idea is pretty simple. You use a language model to basically grade every single row of data in Fineweb. And then you filter those out, the highly scored ones, and that gives you Fineweb Edu. So let's take, you can take a quick look at the prompt that's used. Here's the prompt from Hugging Face. Here's an extract from a web page. Evaluate whether it has high educational value and could be useful in an educational setting. And it's scored on 0 to 5. So there's 1 point for basic information about educational topics. There's a point if it addresses certain elements pertinent to education, but does not align closely with educational standards. So maybe it mixes educational and non-educational, maybe entertainment, I don't know. A third point, if it's appropriate for educational use and introduces key concepts relevant for schools. A fourth point, if it's highly relevant and beneficial for a level not higher than grade school. And then a fifth point, if it's outstanding in its educational value, perfect for primary or grade school. And you'll notice here that it's kind of targeting grade school level. And this is something empirically that if you try to tackle data that is too advanced, I think the problem is, let's actually check out the blog. So we'll say grade school or middle level. Well, one of the issues is it becomes very technical. So it'll find papers like archive abstracts and submissions. So to make it kind of more understandable, it seems to be beneficial to target it towards grade school and middle school. Now, I don't know. It seems to me like there probably are ways that you could get it to be more detailed, or I'm not sure. But this is a good stab and it seems to lead to an improvement in performance. Well, we're going to go with it because we didn't do the study and we're just talking about the study. So that was the prompt. And I'll just show you a quick test here of how that prompt works. And I have tested it out on a random page from Wikipedia. I just copy pasted some text. So I have the same prompt. Here's an extract from a web page. I've got the grading, and then I've put in the grading, which is about a landslide. I copied an article about a landslide earlier today, and it describes everything in Wikipedia style. And at the end of that example, it will then ask the language model to justify the score with 100 words and give an educational score. So here's those roughly 100 words. And here's the educational score. So 4 points. And so you can imagine this being used all the way across all the data sets. But there's a problem to that, which is if you want to filter 20 trillion tokens of data, and let's say it's 50 cents per million tokens, which is around the price of GPT 3.5, that's going to cost you $100 million to process all those tokens. So that's not a particularly scalable approach. And therefore, it makes more sense to just do this on maybe 500,000 prompts and train a classifier. So the idea here is, let's not do this on all 20 trillion tokens. Let's just generate 500,000 annotated samples. So in other words, do what I just showed with ChatGPT, but only on 500,000 samples, and then train a classifier. So the classifier is some kind of a neural net that's obviously going to have to be small, because otherwise you're not going to save on cost versus just querying GPT or some other model. So you need to train a small classifier, and you can train it on those 500,000 samples on a score of 0 to 5. And you can find the classifier. It's up on Hugging Face here. So they've also open sourced it. We can check out the size. It's about half of a gigabyte. So it's not an absolutely tiny classifier. It's about half the size of tiny Llama. And we can even take a look at testing this classifier. So I've put together this notebook here. I've installed transformers. I've downloaded the classifier that I just showed you, and I've moved it onto CUDA, onto a GPU. And I've then printed the model just to show it's actually a BERT model. So this is a multi-layer transformer with 12 encoder layers that include attention. And after attention, you can see there's a linear layer, there's some norming, there's another linear layer, then there's an activation function, another linear layer, and some norming. So it's a bit like attention followed by some linear layers, including an activation layer within them. And at the end, there's a pooler. And what this pooler does is it takes all of the information and it channels it into the prediction of a score that's going to be from 0 to 5. And you will train that by back propagating on the scores of 0 to 5 with the data generated from Llama 370B in the case of the Fineweb Edu dataset. So here's my same text, and I've just put this text into the model to see if the classifier works, and it's predicting 2.49. So it thinks it's, not a bad piece of data set. And notably, this is lower than what ChatGPT thinks. Now, granted, ChatGPT is a different model. It's GPT 4.0 or 4.0. It's not Llama 70B. So it's not exactly correct for me to compare what ChatGPT thinks with what the classifier based on Llama 370B thinks. Furthermore, the classifier won't be perfectly accurate, so it's not going to align exactly with what the model itself would say, because it's obviously trying to take a shortcut in how it's classifying the answers. I thought maybe it's because the prompt is a bit messy at the start, like this data, so I cleaned up the prompt a bit to see if that would help improve the score, and I got 2.52, so it increased very marginally. So yeah, I'm not able to get the classifier to predict 4 out of 5, but it could just be because the classifier is based on Llama 370B, and also it's just not as accurate as the model itself. Either way, using this classifier is going to be a lot faster and allow you to get through 20 trillion tokens worth of data a lot faster than using a full language model for querying. So that's what Fineweb does. And after it goes through this classification step, the dataset is reduced from 15 trillion tokens, which is the base Fineweb, down to 5 trillion. So a reduction of about 66%. And that is what allows for the performance improvement that we see here in getting up to the pink line. And this is not insignificant. I mean, it's a difference of about, 0.02 in terms of the aggregate score. And I mean, that level of difference is actually bigger than the difference in the quality of data sets from 23 up to 24. Not sure that's the right benchmark, but it's one benchmark just to think about this difference in performance as being fairly meaningful. So you've now seen the full pipeline. I've taken you all the way through the basic pipeline. I've taken you through how to further filter using a language model. And the last thing I want to do is make a recommendation on which dataset to use for training. And my recommendation is Fineweb Edu, but more specifically, take out only the latest crawl. So let me describe that in a little more detail. I've already explained how we have Fineweb. It's not shown on this slide, but back here I showed Fineweb. It's a 15 trillion dataset. Fineweb Edu is 5 trillion in size. And what I'm saying now is, rather than training on the 5 trillion dataset, which includes all of the dumps, what you might like to try is just grabbing the most recent dump. And that, I haven't downloaded it, but I expect it's going to be somewhere maybe in the 50 to 100 billion token range. And why would you do that? Well, we talked about earlier how if you deduplicate across all the dumps and you just keep one copy of the documents, you actually get kind of worse performance. So this is uncertain, but to me it suggests that if you consider the extra data that's in the older dumps, that's not in the newer dumps, you may to some degree be worsening the quality of your data. Now, furthermore, just because you're considering all of the dumps together without deduplication, it means that you have lots of copied data. So you might think you're operating on a data set of 5 trillion, but really that data set is very heavily duplicated. So you might be better just to focus on the latest dump and train for multiple epochs rather than using the full 5 trillion data set. Now, I'm not highly confident on that because you'd need to run the ablation study on the full 5 trillion and compare that to running with a similar or lower number of epochs on the 50 to 100B. But I think there is initial reason to guess that might be the case just because deduplicating across all of the runs or all of the dumps tends to give worse performance. And so hopefully after seeing the data pipeline, especially with the language model assisted filtering, you can understand now why Llama 3, purely by improving the data quality, is better than Llama 2. In essence, by doing some filtering using a language model, whether that's through a classifier or just direct filtering, if you've enough money, maybe like Meta, then you can filter out the better samples within that data. And with better samples will come better performance overall. The performance improvement in Fineweb when it goes to the educational version is significantly better than the Fineweb base version. And you can see how it was quite difficult to improve over the C4 dataset, but just adding in that language model filtering made a significant improvement. That's not to say there aren't any other techniques being used by Llama 3 or indeed Phi 3, which uses even less data for the same effects. There are other techniques like k-means filtering that can be used to balance the data set, something I might talk a little bit more in about later videos. So that's it for the pipeline today. Let me know any questions below in the comments. Cheers.